Hi, y'all. All right, let's talk about the gamma distribution a little bit and the gamma function in particular. But before we do that, I wanted to talk a little bit about this, the so-called memoryless property of the exponential distribution. Okay, so if x has the exponential distribution with a particular parameter lambda, then the probability that x exceeds t plus some fixed number t0, given that x was already bigger than or equal to t0, is going to be equal to the probability that x is bigger than or equal to t. So really, it was almost as if like waiting for t0 amount of time was irrelevant. If you're given that it was beyond t0, then it was almost like you were starting the clock over, and you might as well have just been waiting for t time. Okay, little t amount of time. So let's kind of visit that a little bit. Okay, so let's go to my iPad here. Okay, and here it comes. All right. So what do we have going on here? We have x is distributed as the exponential distribution with parameter lambda. Okay, we know lots of stuff about that. So we want to know what is the probability that x is bigger than or equal to t beyond t0, given, hang on a second, let me erase this, okay, given that x was already beyond t0. Okay, well, what about that? Well, that is going to be equal to the probability that that x is greater than or equal to t plus t0, and x is bigger than or equal to t0. And by the way, we're assuming that all of these things like t and t0, this is only interesting if these things are equal to or greater than 0. Okay, because remember, x is a random variable that only takes on non-negative values anyways. Okay, and this is down here, this is divided by the probability that x is equal to or greater than t0. All right, fair enough. Well, do you see, I mean, what about the top? What about the top, okay? The event x is bigger than or equal to t plus t0 and x is bigger than or equal to t0. Well, do you see that this event right here implies that event, okay? That the event that x is bigger than or equal to t plus t0, well, x is automatically going to be bigger than or equal to t0, okay? And that is what's true about these events. This event here, the event x is bigger than or equal to t plus t0, is contained in, okay, is contained in this event right here, okay? And therefore, when I take the intersection, the smaller of the two events is going to take over. And in this case, that would be x bigger than or equal to t plus t0. So this is equal to the probability that x is greater than or equal to t plus t0 divided by the probability that x is greater than or equal to t0. Okay? And remember, well, hang on, let me go back. Let me go back and remind you of some stuff. We were messing with the probability that x is bigger than or equal to little x. Okay, remember this? We did this in our last video. The probability that x is bigger than or equal to little x is just e to the minus lambda x, e to the minus lambda x. Okay, that's for any given x value, okay? So let's use that to our advantage over here, okay? So we're here. Okay, we need to compute those probabilities. We know how to compute the probability that x is bigger than or equal to anything. It's just e to the minus lambda times that anything. Okay, so let's go to the next page. So this is equal to oops, equal to e to the minus lambda t plus t0. Okay, that's kind of like our little x, divided by, remember on the bottom we have the probability that x is bigger than or equal to t0. So this is e to the minus lambda t0. And do you see that this guy down here is going to cancel with this guy right here? Because I could split up that exponential in the across the powers, okay? And so this is going to end up being e to the minus lambda t, which, by the way, is equal to the probability that x is greater than or equal to t, right? So x, in some sense, has forgotten about the fact that it's already waited t0 amount of time. That's what the memoryless property is for the exponential distribution. Okay, so that's fascinating, I think. That's fascinating. Okay, so that's why we have this, going on over here, the memoryless property. Okay. So moving on. What's going on here? Okay, we already did that one. I want to talk about the gamma function a little bit. Okay, so the gamma function is defined by this, and there's a couple of claimed features of the gamma function. So first of all, you know, gamma of alpha, alpha just has to be something bigger than 0. Okay, so gamma of alpha is defined by that integral, and alpha just appears as the power of in the power of x inside the integrand of this thing. Now, because we have exponential decay, and we're in x is bigger than or equal to 0, and you have that e to the minus x, that's going to crush x to that power so badly that this integral will indeed converge. Okay, so we don't have any concerns about convergence of this integral. It will happen. Okay, but let's talk about this thing. Okay, so here we go again. Yeah. Okay. So here we are. Let's go to a new page here, and we'll talk about the gamma function. So what did we have? We had gamma of alpha is equal to the integral from 0 to infinity of x to the alpha minus 1 e to the minus x dx. Okay, and that e to the minus x is what keeps this thing under control. Okay, so for instance, let me just you know, write this. So like, what if I wanted to compute gamma? And incidentally, this thing is only right. We only consider it for alpha bigger than 0. Okay, for alpha bigger than 0. What about gamma of 1? That's a pretty easy one to deal with. So gamma of 1 is equal to, now gamma of 1, that's just going to kill the power in that x, and that's going to be the integral from 0 to infinity e to the minus x dx. Okay, what is the antiderivative of e to the minus x? Well, that's minus e to the minus x, and I'm evaluating this between 0 and infinity. The infinity part goes to, right, e to the minus infinity, like e, if x goes to infinity, that goes to 0. Okay, that goes to 0. And then I go minus negative, which is plus e to the 0, which ends up being 1. Okay, so gamma of 1 is 1. Okay. Now, what about other values of gamma? Okay, well, let's do another one here. What about, let's do another page here. What about gamma of 2? Well, that's going to be the integral from 0 to infinity of what? Of x to the 2 minus 1, which is 1, e to the minus x dx. And you say to yourself, uh-oh, I've been here before. This looks like it's going to require integration by parts, and you would be absolutely right. So you put u equal to x, you put dv equal to e to the minus x dx. Okay, I'm running out of room over here on the side. E to the minus x dx. Then du is just dx. And what is v? V is negative e to the negative x. Yeah? So this thing equals, what is it going to be? U times V, which is negative x e to the negative x, evaluated between 0 and infinity. Okay? And you go du v. So it's minus the integral of v du, but there's a negative sign there, so that gives me a plus the integral from 0 to infinity of what? Of e to the negative x dx. E to the negative x dx. Now, the thing that's interesting is that 0 to infinity, like I have negative x e to the minus x evaluated between 0 and infinity. E to the minus x is going to destroy that, even though that x is going to infinity, e to the negative x is going to 0 way faster than x is going to an infinity. So that's going to go to 0. And of course, plugging in 0 into that gives me 0 as well. And so I simply end up with, this being equal to the integral, so this was gamma of 2, right? Gamma of 2. This thing just ends up being equal to the integral from 0 to infinity of e to the minus x dx. And you might say to yourself, well, that looks a lot like what I just did, right? A minute ago, and that was 1. Okay, so gamma of 2 is 1, and you say, wow, what's going on here? Okay, well, I don't know. Let's try gamma of 3. Okay, gamma of 3. What's that? Well, it's the integral from 0 to infinity x squared e to the negative x dx. Okay, and we do integration by parts again. You put u equal to x squared. dv is e to the negative x dx. Okay, du is 2x dx, and v is negative e to the negative x, just like we did before. Okay, and we do integration by parts. Okay, it's going to be negative x squared e to the negative x, evaluated between 0 and infinity, minus negative, which is plus. This time there's a 2x there, so it's plus 2 times the integral from 0 to infinity. What? 2x e to the negative x dx. And you say, well, the x squared gets whipped by e to the minus x as x goes to infinity, so that goes to 0. Plugging in 0 gives us 0. Okay, and what do we end up with? Well, glad you asked. We get that gamma of 3 is equal to 2 times the integral from 0 to infinity x e to the negative x dx. And don't forget what we just did a few minutes ago. That is this guy right here. That's just gamma of 2. Okay, so gamma of 3 in the end ends up being 2 times gamma of 2. Oops. 2 times gamma of 2, which is 2. Okay, and I am telling you, in this way, if you do like gamma of 4, you will similarly obtain, because you'll do integration by parts, like you'll have x cubed in the as the integrand. If you do gamma of 4, you'll do integration by parts. You'll get 3x squared, and that 3 will get pulled out of the integral, and you'll end up getting 3 times gamma of 3. And in fact, this works no matter what alpha we do. We get that gamma of alpha is always equal to alpha minus 1 gamma of alpha minus 1. Okay, so for instance, if you have something like gamma of 7, this will be 6 times gamma of 6, which will be 6 times, okay, you invoke it again on gamma of 6. This is 5 times gamma of 5, okay? And then, you could say, well, all right, so how far down is this going to go? Well, it'll go down, it'll be 6 times 5 times 4 times 3 times 2 times 1, times gamma of 1. Okay, and what's gamma of 1? Well, that's just 1. And then, so notice gamma of 7 is 6 factorial. Okay, so that's what I meant before when I was talking to you guys about the fact that the gamma function is really just an extension of the factorial function. Okay, but the argument, the thing inside of the gamma function is one higher than the thing you're taking the factorial of. So this all comes from this identity that gamma of alpha is simply equal to alpha minus 1 times gamma of alpha minus 1. Okay. So, so that's an interesting feature of the gamma function. Now, there's some other features that that were in here that we wanted to be aware of. For instance, well, gamma of n is equal to n minus 1 factorial. There's a special value. There's a special value of gamma at 1/2 that's especially important to us, and that's equal to the square root of pi. Okay, that's equal to the square root of pi. And it turns out that will come up later on. I'm not going to go into the details of that now. It turns out that requires a little bit of multivariable calculus to pull that off in full detail. So we'll leave that one alone for now. Okay, but let's look at this. Continuous random variable x is said to have a gamma distribution if the probability density function of x is given by that. Okay, is given by that. Now, again, gamma distribution has two parameters. One of them is alpha, and one of them is beta. Okay, and I promised before that what's really going on here is essentially that we're waiting for the alpha occurrence. Now, look, we don't necessarily require that alpha be an integer. That's part of the beauty of the gamma distribution and the gamma function itself. But in order to aid our understanding, it's sometimes convenient to think of alpha as being an integer. Okay, so here's the thing. So watch this. You know that the moment generating function is basically the fingerprint for a given distribution. So I'm going to show you that distribution I just defined, namely that we're waiting for the alpha occurrence, it does have that moment generating function, and therefore the gamma distribution is connected to that. Okay, so I'm going to go back over here and show you just that. Okay, so back to this, share, okay, screen mirror, here it is. Okay, so here we go. What do we want to do here? So suppose that y, well, okay, I'll use x. Suppose x is equal to x1 plus x2 plus dot 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 plus x alpha. Okay, alpha is an integer. Okay, so alpha is a positive integer, alpha in z plus. And suppose that each of these xi is distributed as the exponential distribution with parameter lambda. Okay, and lambda, the relationship between lambda and beta is that this is just 1 over beta. Okay, 1 over beta. What is the moment generating function of this x? Okay, the moment generating function of this x value of t is going to be the expectation of e to the t x. Okay, so let me just write this: x1 plus dot 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 plus x alpha. Okay, and then basically I can break this thing up into various exponentials and then use the independence of the x whatevers, right? I'm assuming that all of these guys are independent. that all of these guys are independent of each other, okay? Those are independent x sub i's. Use the fact that they're independent to kind of break up the expectations. So this is going to be the expected value of e to the t x1 times, right, and I multiply all these together, right, times e to the t x alpha. Okay, well, look, all of those have the same moment generating function. Okay, the moment generating function is 1 over 1 minus t over lambda. Remember that? It's 1 minus 1, right? So this is going to be something raised to the alpha, because they all have the same moment generating function. So it'll be 1 over 1 minus t over lambda. Okay? There's alpha of those. And you say to yourself, okay, 1 over lambda is the same as beta. So this is like 1 over 1 minus beta t, beta t raised to the alpha, okay? So that means the moment generating function of this thing, which is simply a sum of these waiting times between occurrences. So x1 is the waiting time until the first observation, x2 is the waiting time from the first to the second observation, x3, et cetera. X alpha is the waiting time from the alpha minus first observation to the alpha observation, gives me this moment generating function. That is the moment generating function. And that is the thumbprint of the distribution. And lo and behold, look over here. That is exactly what we have. That is exactly what we have here. We see this moment generating function sitting right here, 1 minus beta t for the alpha. 1 over beta is equal to lambda, yes? And of course, x is the sum of x1 all the way up through x alpha. Okay, and each one of those has expectation 1 over lambda. So it's going to be alpha of those times 1 over lambda. But 1 over lambda is beta, okay? And I have this variance as well. Like the variance before was 1 over lambda squared, which is beta squared. And if I have a sum of independent random variables, I can just add their variances together. It's going to be alpha times beta squared is the variance. Okay, and why does this thing integrate to 1? Okay, this thing right here, why does this thing integrate to 1? Well, let's check that out. Okay, so let's go over and look at that. Oh, and by the way, notice if I take this density right here and I plug in alpha equal to 1, what do I get? If I plug in alpha equal to 1, gamma of 1, that's just 1. If I plug in alpha equal to 1, that kills this x term right here. Okay, and I'm going to have 1 over beta, because alpha is 1 over beta e to the minus x over beta. But that's the same, 1 over beta is lambda. So this thing is just lambda e to the minus lambda x, which is exactly the exponential distribution with parameter lambda. Okay, so you can kind of see that this distribution right here is exactly an extension of the exponential one. Okay, well, let's just check. You know, one last thing I'm going to do in here about this is to just simply check that this thing is indeed a distribution after all. Okay, so let's share my iPad once more, and then we'll call it quits on this little bit for now. Okay, so here we are. So let's see. Okay, what do we have? So I want to compute the integral, okay, the integral from 0 to infinity of, it was 1 over beta to the alpha, gamma of alpha, x to the alpha minus 1, e to the minus x over beta dx, okay? I want to integrate this, and I want to show that this thing is indeed a distribution, okay, that it integrates to 1. Okay, so again, alpha is bigger than 0, and so is beta. Alpha and beta are both bigger than 0. That's kind of the requirement here, okay? So what I'm going to do is I'm going to put y equal to, I'm going to put y equal to x, x over beta. Okay, I'm going to put y equal to x over beta. Okay, so I will do that in a minute, but let's first write it this way. So this is the same thing as 1 over beta. I'm putting a beta down here. The integral from 0 to infinity. In fact, I'm going to put, hang on, let me erase this right here. I'm going to do a little bit more than that. I'm going to pull out the gamma of alpha as well. That's a constant, isn't it? So this is 1 over beta gamma of alpha. I pull out those constants. Okay, and then how many betas are left? Well, alpha minus 1 betas, right? So it's going to be x over beta to the alpha minus 1, to the alpha minus 1. Okay, to the alpha minus 1. E to the minus x over beta, right? I wanted to just write everything in terms of x over beta. So I'm about to make a substitution. Let's put y equal to x over beta. Then what is dy? Well, it's equal to 1 over beta dx. Okay, so dx, in other words, dx is dx right here. Dx is just beta dy. Okay, and what do you see? This beta over here like cancels with this beta over here. And of course, the y is equal to x over beta, so that's going to really simplify things quite a bit. So the betas cancel completely, yeah? It's going to be y to the alpha minus 1, because y is equal to x over beta. It's going to be e to the minus y, and it's going to be dy. If x is 0, so is y. If x goes to infinity, so does y. So this ends up being equal to 1 over gamma of alpha, the integral from 0 to infinity, y to the alpha minus 1 e times e to the minus y dy. Okay? And lo and behold, this thing right here, this integral right here, what is that? Well, that's gamma of alpha. And this cancel, and we get 1. Okay, so that's remarkable. This thing is a density. It integrates to 1. It's always equal to or greater than 0. And we've already seen that the moment generating function, the moment generating function that is given for this thing is exactly arises from just taking a sum of alpha exponential waiting times between occurrences. Okay, and so we see that the gamma distribution is indeed a natural extension of the exponential distribution, and is just a waiting time for the alphth occurrence in a Poisson process with parameter lambda. But don't forget that the beta parameter in the gamma distribution is related to the lambda parameter in the Poisson distribution by the formula lambda is equal to 1 over beta, or beta is equal to 1 over lambda. Okay, that is all I have to say about that. So see you later.